Welcome everyone. Thank you for coming to this evening's RENA Victoria technical presentation. I'm Tom Delling, the chair, as I guess most of you know. The presentation this evening is challenges in developing offshore wind in Australia by Carra from AMOG and Ralf Skowronnek.
Correct.
Yeah, from Skowronnek and Victorian. Okay. So Chris is the Director of Offshore Energy at AMOG and has over 35 years of engineering experience, particularly with floating systems and in both the traditional and renewable energy sectors. Having previously held senior positions at BHP and with major contributions to the conceptual design of BHP's floating production systems, over recent years, Chris has been extensively involved in advancing the understanding and practice of mooring integrity management of floating production systems and the implementation of risk-based inspection methods. With qualifications including an MSc in renewable energy technology, Chris is now leveraging his extensive offshore energy expertise in the renewable energy sector. He's been involved in recent studies on the reliability of mooring systems for floating wind turbines and is heavily involved with a number of the subcommittees of the WFO, which, if I'm right, is the World Forum Offshore Wind. Yeah. And a bit about Ralf. So Ralf has worked as an insurance engineer in the power and utility and construction insurance sector since 1993. Mm-hmm. This has included from 2007 to 2018, holding international positions at Marsh, who, again, if I'm right, are a global insurance broker and risk advisor. I've had to look some of these up. As renewable energy practice leader, Continental Europe, and head of claims Germany. And since 2019, he's been running his own company, Skowronnek and Victorian International Risk and Insurance Advisors. In his various roles, he's designed risk strategies and successfully placed insurance for major renewable energy and infrastructure projects. Ralf was part of the advisory group Acceleration of the German Offshore Wind Grid Connection, advising the German government. He's also chair of the WFO Insurance Subcommittee. Having gathered experience from more than 37 gigawatts of offshore wind projects in the past 15 years, Ralf and his joint venture partner, Barbara Victorian, who's also here with us this evening, are now providing options that would enable offshore wind in new markets such as Australia to be covered by insurance. So I think you can see from that they're both highly qualified to talk on this topic. So I'm going to hand straight over to them. Thank you.
Thank you very much. Excellent. So thank you very much for taking the time this evening to come and listen to us. I'm very pleased to be able to present this talk in conjunction with Ralf. Ralf brings extensive experience in the offshore wind area, both on fixed structures and also now into the floating wind systems area. So Ralf and I have been involved in quite a number of discussions over the last couple of years in the various subcommittees of the World Forum for Offshore Wind, and taking this opportunity to, while they're visiting Australia, to come and make this presentation. So tonight what we hope to do is to run through a little bit of the background in terms of the growth of offshore wind and how that's moving from fixed into floating considerations now. And then we'll talk a little bit about some of the how you actually take these technologies into a floating space, and then look at the challenges as we start to take this industry from, I guess in terms of Australian context, from the very initial stages, and in Europe from the very first stages of some of the pre-commercial floating wind farms, and to look at what challenges lie ahead. And then we'll talk quite a little bit about how we mitigate the risk. So it's both risk in terms of execution, and then also minimisation of loss in operation. So there are some quite significant challenges, and then looking at those in the Australian context, given that we're quite a way away from various centres of, I guess, vessels and typical offshore fleets that may look to support this sort of industry. So then we'll just do a little wrap up. So I think Ralf is going to first talk about the global scene.
Yes, thank you. And hello to everyone also from my side. So, and thank you very much also for the Royal Institute of Naval Architects for this opportunity now. We really are keen to discuss very early with you guys and also with the people from the wind energy business in Australia, because we think exactly at the beginning now, and Australia is at the very early beginning of offshore wind. We can, from the design phase of projects, already do a lot of good stuff, which is reducing costs and also, yes, from our experience, also reducing some of the claims which otherwise would occur. So to avoid some of these things we did in Europe or in these territorial waters of Europe in offshore wind, not to do in Australia, or to be a little more innovative, is also one of the reasons why we are standing here today. So coming from the global context, the global offshore wind cumulative capacity is really will be a big success story, definitely, and it is all based on decisions which now already have been taken by the government. So you can see that that our numbers are extremely increasing since 2010. At the moment, in worldwide, we have around 37 gigawatts of wind generations at the end of 2022. So here I see the 30 gigawatts 2021. Then from which 10% are wind generation offshore. We have 215 offshore wind farms in operation. We are very often not talking about the Chinese content, but the Chinese content is getting much more important because the Chinese, due to their vast capacity driving what they are doing, they are more going into serious production, which is with the turbines, for example, gives them the chance to increase. In Europe, we have some problems because the numbers of turbines which is being built is lower than in China. So the Chinese are really making it up. 17 gigawatts, yes, are currently under construction, as you can see. At the moment, we are mainly talking about this fixed foundation. So we have two foundation types which have finally won the race. So we had some more 15 years ago, 20 years ago. The major foundation types are now the monopile and the jacket. Some years ago, 20 years ago, we had the tree pile, tripods, so a lot of other things, but these structures were too difficult to produce from a welding perspective. We also have some gravity-based projects in France, a big one now, always also very interesting, perhaps also for Australia, made from concrete, also very cost effective. So a lot of things are now going on, and yeah, this could be the same in Australia. So the Australian opportunity, as we were describing in the slides, is very good because we have, as you can see from the colors, exactly in these regions where already also the wind farm developments are planned, we have very good wind conditions. So the going offshore, the limitations on available onshore sites, and extensive network upgrades and the other things are something which I think you wanted to explain on this slide. So what's this?
Sorry, in the Australian context.
We did agree this morning who would work on which slide. So I will continue with you. Okay, then I will continue with that. If we are going offshore now in the Australian context, we have to take into account that we should do it as simple as possible. So this will be also the message of today. We have some environmental pressures, which means that also Chris explained to me also that we have some new decisions also from the court in Australia, which come when it comes to also the processes, who has to be asked, which parties have to be asked until it comes to a consent of wind farm. So a lot of more parties involved in the future also. Then it could be the case that when it comes to bottom fixed offshore, so we have this differentiating between bottom fixed and floating. How long are we able to build up these bottom fixed wind farms because of our how many shallow waters do we have? So bottom fixed most probably will be economically feasible until a maximum water depth of 60 meters, maximum 70 meters water depth, because otherwise the foundations will be too big for the single turbines. We will see how this will increase. So because 10 years ago I also would have never thought that we would have 15 megawatt turbines. So the same. So you never know where this ends. We have offshore winds, of course, with higher strength and lower turbulence, which is the advantage with respect compared between offshore wind and onshore wind. So, which means that all the wind farms which are now working offshore in Europe and in the European waters have a much higher so-called capacity factor than the onshore wind turbines are bringing. So it really makes sense to go more on in the offshore context, and it definitely really makes sense then as a next step also for today to consider to go into the deeper water, which would mean floating offshore as a next step. From the turbine development, yeah, we can see that at the moment the biggest ones are under development at GE, Vestas, and Siemens. But really the biggest ones at the moment, which has already been built and is in the testing phase at the moment, is the 18 megawatts of Mingyang, China. You can see that this is important for the whole logistics process when you're talking about offshore wind. Which vessels do I need? The megawatt classes, with the megawatt classes, we have always increased the hub height. This is one of the topics, for example, which we could discuss also later today, if you like. How, for example, in auctions from the beginning, the government could positively influence the existing logistics in a certain country, because, for example, one example could be if you would, from the beginning in the government, which never is done, you would limit the hub height to a certain meters, for example, 120 meters, and everyone would have to bid for a turbine with a maximum hub height of 120 meters. You would have much more vessels available, for example. So it's one of the things. No one is doing this at this stage. But perhaps in the future we will come to solutions like this already from the auction. With rotor diameters up to, as you can see here, the 15 megawatts at the moment, the biggest one. So the biggest one is the 18 megawatt from Mingyang. And the second biggest one is at the moment the 14 megawatts live from Vestas, and 240 meters rotor diameter, which means if you are deducting the rotor as such, around 10-12 meters, then you have a rotor blade with 120 meters, or no, 110 meters to 150 meters length, one blade. Also a big logistics problem later. So this is the growth of the turbine during the last years, and until now it looked like as if this would never end. So because every 2 years there is someone bringing out a new and bigger turbine. So a real technical evolution. In floating offshore wind, we have a similar evolution, and it's going on really fast, because the first demonstrators had 2 megawatt turbines around 10 years ago now, the first ones. And now in the meantime, the pilot projects which are running, for example, Hyde in Scotland or King Carra in the UK, they're using 9 to 10 megawatt turbines already on floating. So this is not the future; it is already running. And we have many different types of floaters at the moment. This is very challenging. So we are already talking about this also in the WFO committees, and we have around 80 floater types. So 80 designers, 80 different designs, 80 different production cycles, and very often, and this is the challenge we have when it comes later, how to finance this and how to bring this into into the stream so that it can be produced, because the financials always, of course, they want to see more track record, or they want now to demonstrate their capabilities with a demonstrator. We don't have enough demonstration sites, for example, worldwide. So this was a topic we already raised 2 weeks ago. So we need more demonstrator sites also. And some of them are already challenging the existing floating structures by bringing in, in their opinion, some more intelligent ideas with respect to mass production, to serial production. So using a very similar concept as it is now already floating, but with some more ideas with respect to cheaper future production. And at the moment, simply we will see how this will go on. This is also one of my jobs as insurance engineer, because for you as a technician, there are some principal rules how this works in project finance, also for infrastructure projects, for metros, for buildings, for everything. So first comes the technology, and you have to build a robust technology to deliver. Of course, also cost efficient, which is always a problem. And then you need financing for these projects. And how can you achieve financing if you don't have the insurance? Because the banks are always asking at which extent this is insurable. So this is one of the roles we as insurance engineers are playing in this game, because we are the translators from the technology providers to the insurers. So we are helping the business to understand, so the finance guys and the insurance guys to understand the technology. So this is my job, for example. In floating, this is brand new, and they need a lot of translators still at the moment. But we have big plans, because in the future, most probably, floating will have a higher capacity worldwide than bottom fixed. So this is a plan. So next slide, please. Yeah, this works. This is from the 22nd of November. DNV made a study about floating wind turbines and how far are they already proceeding with respect to track record. So, and we have, without naming them, we have, the DNV has divided them to the different technical readiness levels. So this is, you see this TRL. So the NASA is using that, for example, but also the offshore energy business is using a slightly different TRL, which goes from 0 to 7. So NASA is 0 to 9. Offshore energy uses 0 to 7. DNV uses the NASA definition, and there are at the moment on TRL 9 level 2 structures. So the semi-subs, which does not mean semi-sub in general. It's 1 or 2 semi-sub types, which the people who are working in the business know who is meant. So one is this, and one is this concrete spar, which are the big spar buoy projects in the North Atlantic. So which are also running at the moment and operating and running quite well. So the semi-subs and the spars are running quite well. The maximum for you as an information, the maximum number of floaters per project still at the moment is 5. So in Carra, 5 plus 1 smaller one, so 5.5. Then in Highwind, Scotland, also 5. Yes. So, and then you can see that there is a big gap in the floater types. So the next floater type we see, the next group of floater types we see is under technical readiness level 6, which means that they are in the demonstrator phase, and they have to successfully finish the demonstrator phase, and before they come then into the pilot phase. And the other ones, all the other ones below, they are TRL 5 and lower. And we all have to speed up this floating offshore wind business in the future, because if we want to achieve our renewable energy targets in the world, we need to be faster than we were in bottom fixed. So in bottom fixed, it was a self-evolution to convince banks and insurance companies about certain level of risk, and we needed in bottom fixed. I think this was within 10 years. It was a very long process because of the track record always. Yeah. And then finally, the business decided to use monopiles and jackets mainly, and the other ones were put away. So, and here we are now at the very beginning, but we don't have 10 years now to consider which floating types we will use. So at the moment, we need a slightly more intelligent system how to work, which Chris will explain on the next slides, what could be done technology-wise to speed up the process, but not to lose safety. So because banks and insurers, they really need this minimum safety level. Yeah, and that's it from my side. Thank you.
That's right. So as Ralf was mentioning, so when we come to Australia, we have quite obviously a very good wind regime down in the southern parts of Australia. So obviously off Tasmania, southern Australia, South Australia, the bottom part of Western Australia, actually even that builds up towards Geraldton as well. So particularly some sites there. And there are a few sites where we do have water depths out to about 60 metres that are also far enough offshore to limit the challenge of visual impact. So, so this is where I guess the step from bottom fixed to floating comes into play, because you've got that restriction of proximity to coastline and viewing points, and then wanting that to be I guess the social driver to push that further offshore from a visual impact point of view, and then that competing with water depth. So as Ralf was saying, that bottom fixed turbines are typically out to 40, 50, 60 metres currently. There's quite a bit of work going on currently looking at, for the next class of turbines, the 25 megawatt class turbines, can we use dynamic vibration absorbers, active and passive means, to actually control some of the structural vibration that these units go once you have a column that's 60, 70 metres tall, standing in the ocean, subject to wave loading and fatigue.
With a nacelle weight of 1,000 tons in the future, in 100 meters height.
So again, large vibrating structures, and that's no different to a lot of the naval architectural issues that you see in standard ship design. So. And then coming off the east coast, I think just last week, the areas off Newcastle and Wollongong, I think, were gazetted for offshore wind in Australia. So the difference there being that typically these areas are going to be in the 100, 150 metre water depth, so they'll be floating to begin with. So talking about the challenges. So again, it's this whole issue of how you execute these projects with minimum risk, and then how you mitigate any loss during production, because these things are going to operate for 25 years. You're going to rely on them from a power production point of view. So how do we manage that? And there are quite a number of challenges. So obviously the key one at the moment is supply chain. So how do you actually build some of these projects? If we take a 1 gigawatt project, that may be 40, 50 individual units. So how do you actually build, ship, fabricate, build, ship, repair, install these units? And how do we have the ports that actually sit alongside that to allow this to happen? And if we go to floating units, then you need more space, because you've got construction of, or maybe the final fabrication of these floating hull forms, and then there's the whole marriage of the turbine towers onto the floating hull form and then placing on the nacelle. So these units are big. If we're talking 300 metre or 250, 300 metre rotor diameter, you can't park many of these alongside each other. So lots of issues. Then we'll talk about costs and how we reduce costs, because obviously this still has to be competitive in terms of the power production cost. And then we'll delve into some of the challenges for maintenance and repair. So the supply chain is a major one. I think Ralf just mentioned a point where we've got 80 different concepts going through, and many of these concepts are looking now at how you can actually mass produce these hull forms and then mass construct them. So so there's a lot of work going on there. When you look from the Australian point of view back into the world market, we'll be a very small portion of that market. So how do we gain access to the shipyards and the fabrication areas in most likely in China or Korea or those sorts of places, to fabricate these structures, how do we actually gain access to those, and then you also gain access to the, to the turbine technology? What can be fabricated here reasonably, and do we have the skill sets here to do that? We spoke about port infrastructure. I'll touch on the next slide. Again, distance from the supply chain, particularly say down in the Victorian context, we're a long way from Singapore, so any shipping is expensive. Any installation vessel is going to have high mobilisation costs to get down here. And once you start to talk about the scale of these projects, then you're looking at some major supply chain logistics problems that will occur during these critical construction phases. And then, of course, do we have the assets here in terms of physical assets and also in terms of the manpower and technical skills to support this type of development? And then how do we attract that and keep that here, as opposed to being dragged into, say, the US, which has now announced a very significant increase in their offshore wind industry. So currently here, I think the government is pointing to the port of Hastings being the preferred site for offshore wind farm developments here. These ports are going to need fairly large marshalling areas for storage. Do we encourage a local manufacturing business here? How does that then link into these sorts of places? Operations and maintenance, how is that going to be handled? And then how do we also balance the style of operations and maintenance work? And we'll talk a little bit about that. So there's a lot of work coming up in the near term in terms of where do we base these sites, given Australia is quite geographically spread. Is there one place in the eastern seaboard, or are there many? So how do we go about that? And how do the various state governments and federal government balance out the bigger picture in terms of making this a feasible industry. In terms of cost, obviously floating offshore currently is about 4 or 5 times more expensive than fixed offshore, and they're looking the next 10 years that gap to close rapidly. And the LCOEs are very competitive. So I think typically the levelised cost of energy for new gas turbine coal-fired power plants are above the current fixed offshore wind costs. So they are competitive. In the Australian context, we'll be a little step up higher again, because now we have to deal with our remoteness and just stretching that supply chain down into this area. So that's going to be a challenge for us. And so it's going to be looking into the things such as standardisation, how we make something that is able to be repeated on scale with low risk. Do we push towards the larger turbines? And as Ralf was saying, that comes at a cost because the newer turbines don't have the track record. So how do we balance that out? And do we put ourselves at, as an operator, do you put yourself at a technical risk because you've got a new turbine operating that may suffer, unexpected issues or failures, and the impacts on those? In the context of an offshore wind farm having multiple units, repeat units with potentially the same common cause type failure modes. So the costing will be a challenge, and there's still a lot of work going on in the industry to address these issues.
Chris, sorry, just when you've got that graph up, do you know what the cost is for solar, which is obviously such a big topic in Australia?
Not Andy Klaus, you might be able to dig that up in the background, yeah. No, I don't have that hand. And then, when we get into the operating and maintenance side, obviously there's these units will be offshore, so there's taking manned access out to these platforms for painting, repair, all of the maintenance that needs to go on to these systems. And also, things such as lightning. So lightning strikes are an issue. And based on European experience, lightning does hit these structures and it does damage the blades. So we're looking at, if we look at some of the lightning density information that's available, the North Sea is fairly low intensity of lightning strike, and it's sort of akin to down off the the southern Victorian sort of area. But once you start going further up the coast and towards into New South Wales, the lightning density changes to be much more akin to that of, say, Japan, where typically it's about 100 times higher density. And so the expectation is there's 1 to 2 blades per year per wind farm that are going to need to be replaced. And for these large turbines, these blades may weigh 100 tonnes. So, and they're 150 metres up in the air, potentially on a floating moving structure. So how do you go about changing these in an efficient manner? And this is a risk that will, it's a given, it's going to happen. So you have to be able to accommodate that.
So we know a lot of things about how it occurs and about the repair costs. We know, and the only difference is the probability of occurrence, which is lower in Europe, much lower. So if you know that someone will occur, and you already know the costs, and you know exactly how much probably higher the probability of occurrence will be, then obviously this is already a case which you really can calculate. But it's not a very nice case for the OPEX, for the operational expenses, because and the guys in the wind farms, they should really take this example into their calculations, which we see at the moment very often is not done. So so this is one of the points also we would like to introduce to you today, and also for the future, where we are also standing for that. We are very often tackling exactly these things. We are bringing the cases from Europe, which translated to Australia will also occur, but the probability of occurrence will be different. So it will be either more often or not so more often. So to bring this in the right context and not only to copy paste from one area to the other.
So in terms of major replacement, as Ralf said, on these larger turbines, the nacelle and rotor mass is typically up around 1,000 tonnes. So a gearbox unit may be certainly well over 100 tonnes to replace. And if these are even on fixed structures, 150 metres in the air, how you actually get those down safely onto a vessel to take back to shore and replace. In various options in the North Sea, where you have access, say, to the big offshore installation vessels. Some of these can do those replacements directly with very large semi-submersible crane vessels. If you're shallow enough water, you may be able to do that off a jack-up. But once we start stepping into the deeper waters and into the floating area, then there are new solutions. So there's a whole raft of new technologies that are now coming onto the market in terms of self-building cranes or self-climbing cranes. So you can attach these to the tower and to climb up the tower. So, and once you get down into the Australian context where you don't have access to these vessels, these types of repair activities are going to be critical about how you approach that and what sort of, I guess, system-wide approach you take to that. For instance, do you share with another developer or another competing wind farm developer an insurance pool for this type of equipment, so that you have that ready if needed, and you can both access that as required. Obviously, the flip side of having good winds down here also means that in terms of the offshore environment, you may not have the best operating environment because the sea states are uncomfortable or limiting, and so the weather windows may be very limited, and you may have quite different production loss issues arising from that because you just cannot get it physically out to do the repair works needed. And
we just had a question come through from the chat asking about the vertical axis turbines with the hub at the bottom. Just well, the question is just what about the vertical axis turbines?
I guess the vertical axis turbines are in development, but again, they're very much down in sort of the technology readiness level. They're very much at the lower levels, and they're probably, I guess they're 10 to 15 years behind.
Yeah, there are concepts with, as Chris said, with a relatively low level, but they are already combined with, for example, also very interesting new floater concepts. So This is exactly what we were talking about before. We will see some floater concepts which have very innovative designs, and this vertical axis is also one of the innovative designs. But you don't know if they will be successful, because we will see if they will be able to manage this critical path on the way to finance and bankability. So they really these companies need venture capital and then private equity before we are talking about bigger projects. So this is the current status of these projects, and they need demonstrators, demonstration sites. A good question.
And also that goes with these units is that the cables, the power cables that connect these units are a big source of failure and a big source of claims. And so there's a bunch of work that does need to be taken into account there. If we come down to Bass Strait, again, there's some quite challenging sea states through here. Bass Strait is very much a bimodal and bidirectional sea state. So we have swells propagating through typically from the west-southwest, and then you may get wind seas from the northeast-southeast coming through from the other side of Bass Strait. And this has caused significant problem to people in the past. So I've got two examples here. One was a heavy lift module on the Yola platform that caused that module to actually be, the lift failed technically, and they had to stop that lift and come back I think it was about 2 years later to actually lift it on properly. And that was all because of the pendulation of that module. Again, 500 tonnes is not dissimilar to some of the masses that we're going to be seeing for these bigger units. Just meeting up with the swell period and the pitch period of the vessels. Another one was to do with ground conditions. Hang on a second. All good. With a jack-up rig that was stuck for about 3 months and unable to get its suction spud cone out of the seabed. And so again, significant risk in those sorts of operations. So there are issues in dealing in these offshore environments that need to be carefully engineered. And then through in terms of moving into the floating, then we're going to be relying very much on the mooring system. So one of the biggest issues that the insurers see is that how do you actually reliably moor these units at site? The experience from the offshore oil and gas industry is that there is a significantly high failure rate, much higher than what you would assume under the design code. So we see significant issues in terms of corrosion, wear, and interaction of dynamic components behaving differently to, I guess, what designers may take from their initial design views. And with the challenge for floating wind and cost is that they're trying to minimise the expenditure. So there's a lot of work going on looking at having essentially a single anchor leg, so per group. So typically on a semi-submersible might only have 3 mooring legs in a Y shape. And can you reliably keep that unit on station with a single mooring leg for that full 25 years or for a period before you need to go and refurbish that? So there's a lot of work looking in the industry at the moment, trying to understand that and what type of technologies may need to be used to actually mitigate these risks, because this will be a common cause failure in that in the wind farm. So every unit has the same, essentially the similar, or very similar mooring system, and they're all going to be subject to similar dynamic contributions. And can you arrive at a failure that then sweeps across that whole system and causes you a significant cost to go and remediate, or hopefully only remediate rather than repair. And I think that's a very good point to hand back to Ralf on.
Yes, thank you. So we have one example which goes into this direction with respect to the operation and maintenance expenses, and how that it is at least as important not only to design for risk mitigation, so to have a robust design, but at least also to, from the beginning in the design, also to implement loss mitigation measures, which, for example, make it easier to reduce the repair costs and the downtime. And we have some actual examples of which we would like to show you. So one of these examples is the Carra gearbox exchange. These are all information which were publicly available in the media. So this is nothing secret here. But here we can see that if I show you what they did, they had a gearbox failure, and due to the gearbox failure, they were not able to tow the floater back to the Edinburgh harbor. Next to Edinburgh here, they had to, because there was a sufficient crane, they had to tow the whole floater with the turbine to Rotterdam in the Netherlands. And finally, this did not last so long. So once the action was planned, after this unscheduled maintenance had been published, they needed 2 months, of course, for the organization. I think also 2 months was very short for an unscheduled maintenance. Yeah? So if you have to manage everything, so to organize the facilities in somewhere, first to have the consideration that you cannot tow it to the next port. So this is number one. I think they needed at least 2 weeks for this until they saw that this is not possible. Then they had to decide to tow it and to get the licenses to tow it through the whole North Sea to Rotterdam. So it was a great job, they did. But what we would like to explain is that it would be better to have repair methods which would avoid these actions, which easily can also happen in the future in Australia. So if you decide to have a big floating offshore wind project, and you decide that you will have one baseboard or really one point which is enough capable also to host several numbers of floaters, then most probably this will not be 5, 6, 7 harbors, because this will be only 1 or 2 probably. So because you have to strengthen the quay sides, so you have to do a lot of things to improve this harbor. And here, yeah, they decided for Rotterdam, and in the future, of course, they will not do that, because in Scotland they will improve some of the harbors, because as you also might have heard, we have this big Scotland bidding round in floating, and we will have other harbors in the future. But I think this is a good example for our next slide, where we have tried to just on one slide to bring this for you together. And I will spare some of the time so that we have also some time for questions later. But what this slide shows is that with some very proper and intelligent work from the beginning, and also between the stakeholders, between the engineers, between the lawyers, between the procurement and the insurance people in a project, you can limit the same scenario. Here's one scenario where we have a serial defect to 30 main bearings. Main bearings is the biggest bearing of the wind turbine in the nacelle, where the rotor is in. And these defects have occurred, so this is no theory. Lead either if you are doing nothing, or if you are working in accordance with certification process and normal contract style. So you have a remaining exposure for the project here of $347 million US. Or if you do something, so I make it very generally, yeah, so you have to do a lot of things, but if you do a proper risk mitigation from the beginning, so I will come to that, and then later also apply a good loss mitigation, then you can lower the same claim to 18. So, and this is a very interesting point. This is what also we would like in the future to provide to Australian clients. How is it possible, and how much does it cost to bring such an event from 347 down to 18? So let's say, to make it very short, in the future it could mean that spend 20 and save to 320. So to make it very simple. For the commercial guys, because this is the most important thing to make this commercially attractive, of course. So here, what did we do? Chris was explaining that there are 2 concepts at the moment under discussion for floating, and of course the second concept, which is the offshore climbing crane and the self-hoisting crane example, at the moment is not so developed because the things are brand new. But companies are considering changing their major component replacement procedure in the future to this type of cranes, which are climbing at the turbine, which are self-hoisting themselves, which means that in our example here, if we are taking the same description, serial defect to 30 main bearings, the big difference at the beginning is that here, with tow to port, for 30 floaters, we need around 2 years, whereas if in the future we use these cranes, which are scheduled and we are fixing them on floaters, we only need 1 year to repair everything. Which means from the beginning it's crystal clear, without doing anything else, simply by deciding from the very early beginning what we will do, and which is very important because you need additional fixing points on the turbine, you need additional certification of the nacelle, so you have to consider this at the very early beginning of such a project. You can already save 1 year of business interruption, so 1 year loss of revenue, which is a lot of money, and which is the major difference here. So here we show that with a very early reasonable decision, we already save a lot of money. And then the second is that it could be the case that once in the future, as Chris said, in Australia, it would really make sense if 2 or 3 projects would decide that, for example, they buy 1 crane. Yeah, because a crane is much less expensive than a vessel. So such a climbing or self-hoisting crane, I don't know how much it will cost, between $5 to $10 million perhaps. I think it's not more compared to a big installation vessel with 300 to 400 millions. It could make sense. So which means this would be in the future the technical risk mitigation, because then immediately, in case that it happens, you have a crane available, you are much faster, and you can much easier make this next to it's no real corrective maintenance. It's much more also not the schedule, but when it comes, you exactly know what has to be done. So then you are using this crane. And what we think is that that as a next step, it would be able even also to convince the turbine manufacturers to extend their indemnification from their contracts, what they are at the moment not doing in floating, to the level how they would also indemnify under bottom fixed. So normally under bottom fixed, this serial defects, if you have negotiated enough limits in the supply and maintenance contract with the turbine supplier, this normally the first full serial defect, if you have negotiated correctly, is fully covered under the contract. So 0 loss for the project. But this is a big difference for the bankability and insurability, that this at the moment in floating is not the case. In floating, the turbine supplier at the moment contractually behaves as if he is only delivering the turbine to the quayside, and then the owner takes it over, and then commissioning and then is done by the turbine supplier still. So he comes back and commissions and operates and start operation, but he doesn't take the risk for non-availability of logistic units. And exactly for this, what costs the majority of money in such a case, he doesn't take the responsibility, which I also can understand from the perspective of the turbine supplier. So this is nothing to blame someone for. It's simply such a big risk, which means if developer in this example and manufacturer are in the future going the same way, it could be the case. I think that the manufacturer can be convinced for bankability cases to take more risk in the contract, also in floating, which would mean we come to this amount. So this is why we wanted to show you today, based on this example, why are we standing here together, the specialists in Australia, the specialists for the energy business, including the components with one of the highest failure rates, which are the mooring lines, and the insurance engineer. Why are we presenting together? Because we are in the future in Australia, we want to do this as project advisory together, because not only to mitigate the technology in the future, from the beginning we want to make a reasonable technical mitigation, which is not so costly, because otherwise it's not done, but which is reasonable, and where we think that it makes financing and insurability easier. And this has to be discussed with the technicians from the very early beginning, and including of course, the naval architects who are working in that business, because they are the enabler also when it comes in the floating projects from the design phase. So how do we want to repair this, and how can we fix this in a very short time?
Okay, well, so in summary, so taking through quite a journey here, but so we do have the opportunity here. We have fantastic wind resource off Australia. We have some strategic locations that give very good access back into the existing grids. So we look through some of the major, I guess, port centres: Portland, Newcastle, Wollongong, even off, it's not that distant from Barry's Beach, or sort of not in Gippsland to get back into the Victorian grid. So there's opportunities there. There's a link to green hydrogen production and export. So there's the ability to provide not just power to Australia, but also to export power to internationally. But our remoteness is going to cause us issues in terms of supply chain and cost. We will be competing against Europe, Asia, and the US. So the industry needs to be cognizant of that, and government as well. As Ralf has been saying, that the bankability of commercial scale projects is going to be heavily linked to its technology and its insurability. And getting that balance right is going to be absolutely critical to taking these forward successfully. And then if we look back in terms of the overall industry here, there's opportunity for transition of our workforces. So if you look into the UK and Europe, transition of the offshore oil and I guess the offshore oil and gas workforces is well underway to go into these spaces. How are we going to do that locally here, and how do we also bring along, I guess, some of the coal and the power industry professionals and skilled tradespeople? How do we actually bring those into make this industry a success? Because the challenge is there. It's going to take a lot of work to get this to be successful, but there shouldn't be any reason why ultimately it should be a success. So I think we've probably covered more than we probably should have.